Welcome to Lecture Online. Now let's answer the question, why does an inductor behave like an inductor? Well, what do we mean by behaving like an inductor? Well, remember that an inductor opposes a change in current. Only the change in current. You can have current going through an inductor, as long as it's DC current, the inductor will do absolutely nothing. Only when that current begins to change, either increase or decrease, the inductor begins to do something. The question is why? Why does an inductor do that? Well, let's try to figure that out. Here we have a single loop. We have a wire going up, around the circle, and coming back down. So we have a single loop of wire here. And let's send the current through that wire. The current will then go around the loop like this. And then if you use your right-hand rule, if you take your thumb and put in the direction of the current, then your fingers will curl in the direction of the magnetic field around any current wire, or I should say around any wire that carries a current. Let's say I have a single wire here that carries a current in this direction. You can then take your thumb, point in the direction of the current, and your fingers will curl around the wire, and the curl of the fingers will show you the curl of the magnetic field. The magnetic field will go around the wire like this. So it's behind the wire, in front of the wire, back behind the wire. So the magnetic field that exists around a current carrying wire looks like this. When that wire then gets put into a circle or a turn like this, then you can see how the magnetic field will go through the loop inside this and then outside the loop on the outside. So we have, if you think about it, the magnetic field comes back out of the loop, around like this, out of the board, and then back into the board through the loop. We're only concerned about the magnetic field through the loop. We can say that there's what we call magnetic flux through the loop. In this case, it's into the board because of the direction of the current like this, and the amount of flux is simply equal to the strength of the magnetic field inside the loop times the cross-sectional area of the loop, however big the loop is. The bigger the loop, of course, the bigger the flux through the loop. The magnetic field inside a solenoid can be calculated to be the permeability of in sometimes a free space or the core, whatever the core is made out of, times the number of loops per unit length of the solenoid, times the strength of the current. Notice that if you double the current, you double the strength of the magnetic field. So the amount of flux, the strength of the magnetic field inside the loop, simply depends upon the structure of the loop and the amount of current flowing through the loop. Now, what happens when you increase the current? Well, when you increase the current, you will increase the magnetic flux because, in essence, you've increased the magnetic field. You increase the current, which increases the magnetic field. When you increase the magnetic field, you increase the flux through the loop, like you see here. And what an inductor does, an inductor opposes that change by setting up an EMF, by inducing an EMF that causes a current to flow in the opposite direction, which then causes the magnetic field in the opposite direction. And so here I'm indicating with the little dots, meaning that the magnetic field induced is coming out this way. So this is the magnetic field that's induced by the coil, by the loop, which is caused by an EMF that's induced, which causes a current to flow in the opposite direction. So now we have an induced current flowing in the opposite direction, which produces a magnetic field in the opposite direction, which tries to stop the current from increasing in the first place. And that's what an inductor does. And during that small brief period in which it sets up an EMF, as long as the current is changing, an EMF is induced, which sets up a current in the opposite direction, which causes a magnetic field that tries to keep the original magnetic field from increasing. So now we can say that the EMF that's induced, there's like a voltage induced on the coil, which is equal to the voltage across the inductor, the V sub L. Remember the equation we showed you in the last video? This was equal to the inductance times the rate of change of the current with respect to time. And the EMF induced, according to what Faraday found out, so Faraday's law is now called EMF induced is equal to the number of loops in the term times the change of the flux through the loop per unit time. So we can put that on the other side. So for the magnitude of that, we have the number of loops times the rate of change of the flux through the loop with respect to time. And of course, the definition of the flux is that's equal to the magnetic field times the cross-sectional area. So here we can say that N times the d dt, the rate of change with respect to time, of the magnetic field times the area is equal to L times di dt. Now, of course, in this case, we're going to leave the loop the same size, so the area doesn't change, but the strength of the B field does change, and the B field can be found by replacing it by this quantity right there. So this can now be written as N times A, because the cross-sectional area doesn't change, times the rate of change of the magnetic field, and the magnetic field of the solenoid is equal to this. So it's equal to mu N I over L, like this, and that is equal to L times di dt. Now, of all these things on the left side of the equation, notice that the permeability is a constant, the length of the solenoid is a constant, and the number of loops is a constant. The only thing that changes is the current. So this can now be written as N times N, which is N squared, times the permeability, times the cross-sectional area, divided by the length of the solenoid, times the di dt, the rate of change of the current with respect to time, is equal to the inductance times di dt. And notice, if you now compare the two equations, notice we have a di dt on both sides, but now we can see that the inductance of the solenoid is equal to this quantity right there. The inductance L is equal to the number of loops squared times the permeability of the core times the cross-sectional area divided by the length of the solenoid. So there's another way in showing you why an inductor does what it does, and from that we can see that the inductance of inductors simply depends upon the physical size, the number of turns squared, the permeability of the core, the cross-sectional area, and the length of the inductor. And that's why an inductor does what it does. It fights the change in the current.